So what do we do if the delay introduced by our critical path is too long and we want to make it shorter? In this network, we have two paths, the first formed by CLB1, CLB2, and CLB3 between the pair of registers above, and the second formed by CLB4 and CLB5. So our critical path will be the longer of the two paths, and the operating frequency or the clock period will be the greater than or equal T setup plus TCQ plus whichever is bigger of T1 plus T2 plus T3 and T4 plus T5. Now, what if the clock period here is too long, meaning that the operating frequency is too low, and we want to increase the operating frequency of this circuit? The answer here is to perform internal pipelining by breaking the critical path or the non-critical path and the critical path, but most importantly the critical path, and introducing registers in between these logic blocks. So we introduce internal registers to perform internal pipelining. In this case, we no longer have two paths. In fact, we have 5 paths, because a path is defined as a combinational path between two consecutive registers. So we have this as path 1, this as path 2, this as path 3, path 4, and path 5. We have 5 paths now. And so, therefore, the operating frequency or the clock period will be greater than or equal T setup plus TCQ plus the maximum of not T1 plus T2 plus T3, but T1 or T2 or T3 or T4 or T5. So we have now broken the path above into shorter paths. Will this make this circuit faster? It will absolutely make it faster. It is certain that this will make it faster. How much faster it makes it depends on the initial delays and how we did the pipelining. So let's just assume delays in arbitrary units. You can just assume the units for delay are 1 nanosecond. And just, for the sake of illustration, in this case, we will assume that T setup and TCQ are both 0. So there are no setup and TCQ delays, which is never going to be the case, but we'll just assume it here for simplicity. And let's assume that T1 is equal to 10 nanoseconds, T2 is equal to 10 nanoseconds, and T3 is equal to also 10 nanoseconds. So we have combinational delays in all of T1, T2, and T3 equal to 10 nanoseconds. We can also assume the same for T4 and T5. Let's just assume that all of them have the same delays. So the original delay before pipelining, before internally pipelining, was T greater than or equal T1 plus T2 plus T3 or T4 plus T5. Of course, the larger delay will be T1 plus T2 plus T3, giving us a clock period of 30 nanoseconds at least. After pipelining, the critical path will reduce to 10 nanoseconds because it will be any of the path. It will be 1, 2, 3, 4, or 5 because all of them are equal, and each of them will be 10 nanoseconds long. So internally pipelining in this case has given us an increase in frequency of 3-fold. But why did that happen? That happened because when we did internal pipelining, the pipeline registers were introduced at such locations that we break down the combinational delay almost equally, right? Or equally in this case. Now, let's assume that when we did pipelining, we introduced internal pipelines between CLB1, CLB2, and CLB3, but we did not introduce such a register between CLB4 and CLB5. So let's assume that we just left it like this, so that the bottom is still one path. So originally, before pipelining, we still have the 30 nanoseconds. But after we did this kind of pipelining, where we only pipeline the above path, T will be greater than or equal T setup plus TCQ plus the maximum of T1, T2, T3, and T4 plus T5. So in this case, T will become 20 nanoseconds. So what happened here is that before pipelining, the critical path was through the top 3 CLBs. When we did pipeline this critical path, we migrated to another critical path which goes through CLB4 and CLB5 only. So to guarantee that we get the maximum benefit from the pipelining we did in the top path, we have to also pipeline the bottom path to get this 10 nanoseconds. So pipelining the bottom path was necessary because even though the critical path was in the top path, we could get a situation where the critical path migrates after we perform pipelining on the original critical path. Also, as I discussed, the benefits we get from pipelining will be highly dependent on the original delays in the original critical path. So let's assume, for example, that T1 was equal to 10 nanoseconds. Same, T2, 10 nanoseconds, and T3, 10 nanoseconds. So nothing has changed here, right? But let's just assume that T4 is equal to 27 nanoseconds and that T5 is equal to 1 nanosecond. So what's happening here? Before pipelining, before performing an internal pipelining, T would be greater than or equal to 30 nanoseconds. It would still go through 1, then 2, then 3 in the top path, because the summation of their delays is 30 nanoseconds. The summation of the path going through CLB4 and CLB5 will be 28 nanoseconds. So before performing internal pipelining, the path through 1, 2, and 3 is still the critical path. Now, after performing internal pipelining, on the other hand, T will be greater than or equal T setup plus TCQ, which is 0, and the maximum of 10, 10, 10, which is T1, T2, and T3, 27 and 1, which is T4 and T5. So T will be greater than or equal 27 nanoseconds, which is an improvement over 30 nanoseconds, but certainly not the threefold improvement we observed when all the paths were originally equal. So whether or not we get a huge benefit from internal pipelining depends on where you did the internal pipelining. So in this situation, how can you improve the results of pipelining? What we can do is actually go into CLB4, break it down, because it is now the new critical path. We can go into it and break it down and ensure that the two sub-modules that are formed from breaking down CLB4 each have equivalent delays. Then we can pipeline between these two sub-modules, and that would be the proper internal pipelining that we should do. So who says that each of these CLBs cannot be broken down from the inside? They can. What we decide to define as a combinational logic block is arbitrary. It could be composed of a single CMOS gate, it could be multiple CMOS gates, but even if it is a single CMOS gate, if it's complex enough to be the critical path on its own, then there is a possibility of breaking it down. Now, let's assume we are at the situation where, the new clock period after pipelining is 27 nanoseconds. And let's assume that we now do have a T setup of 1 nanoseconds. What this means is that by the second clock edge of the clock, this is the second clock edge, the output from path 1 and the output from path 2 and so on until path 5. So we will draw the outputs of all the combinational path and try to figure out when they are ready. So by output of a combinational path, we mean the input to the next register, so these nodes. When will these outputs of the combinational blocks be ready? You can also assume that TCQ is still 0 volt. So we assume that the clock period is 28 nanoseconds. So T is greater than or equal to 28 nanoseconds, 27 nanoseconds from the delay of CLB4, and 1 nanoseconds from T setup. So what we know is that CLB4 will be ready just 1 nanosecond before the clock edge. This means that it will be registered properly because it is ready a setup time before the clock edge. Why do we know this? Because that's how we calculated the clock frequency. This is the critical path, and the clock frequency is just enough so that the critical path reaches the output register just in time to respect setup time. But all the other paths will be ready earlier than this. So for example, path 1 will be ready at 10 nanoseconds, after 10 nanoseconds, which means it is ready before the active edge by 18 nanoseconds actually. So path 1 will be ready 18 nanoseconds before the active edge. It needs to be ready 1 nanosecond, but it finishes 17 nanoseconds earlier than path 4. Now, path 2 is going to be the same as path 1. It's going to finish at the same time, and so does path 3. Path 5 is going to be even earlier than these guys. So these guys each have 10 nanoseconds of delay. This has only 1 nanosecond, which means that it is 27 nanoseconds early, right? So it's basically 9 nanoseconds earlier than any of these guys. So path 4 is going to be ready just in time. Path 1 is ready ahead of time. How much ahead of time? Not 18 nanoseconds, 17 nanoseconds, right? It's 18 nanoseconds before the active edge, 17 nanoseconds before it needed to. So is the case for path 2 and path 3. Path 5 is going to be ready 26 nanoseconds before it needed to, before T setup. And so what do we call these times? I mean, these times seem significant, how much ahead of time each of these paths is ready. As we discussed earlier, the fact that they are ready early is not a bad thing, at least so far, right? So we call these slacks. So slack is the amount of time that a signal is ready ahead of when it needed to. By definition, for the critical path, slack should be 0. So slack for path 4 is 0. So this is 0 slack. For all the other paths, slack will be positive. So all of these have positive slacks. How much? Depends. Like path 1 through 4 have 17 nanoseconds of positive slack. Path 5 has 26 nanoseconds of positive slack. So could we have negative slack? The answer is yes, and this is what we will talk about in the next video.